very successful partnership with Microsense in pushing the thermal analysis to the next level. And that next level is to take into account the antenna, creating the link between thermal dissipation and electromagnetic radiation. That would foster a holistic vision where the integrated circuits, the packaging, the PCB, and the antenna are treated in one single vision. And that single vision is very suitable for industrial testing.
You don't need to put at the side. Yeah, you don't need vibration. You don't have vibrations.
Microsense system. You see, this is the optical pass. When we do probe-to-pet alignment, but after we complete probe-to-pet alignment, so we switch to Microsense system, and then we could do real-life measurements. So we have here devices from Ferdinand Braun Institute provided to us. It's a high-power ham transistors, and once it's setting up the live demo. Okay.
Now, Microsense uses this very unique technique of hitting the sample with photons in a green wavelength, and the return photons from the sample have some correlations with the temperature of the material itself, and there is some synchronization and there is some laser pulsing that happens to do all that. Now, that camera is essentially in the visible range, so using the same lens and having two different cameras, you can now not only look at your wafer, you can look at your probe, you can look at your positioners and do automated landing, but you also get the temperature gradient across the sample, but you're getting it at optical resolution. So now you can see gates and you can see device temperatures directly on there. And if you look at over here, that green light that you see, that's of course from the Microsense system for thermal, but you can see the substrate very well. Now, to combine this thermal measurement, the automated setup, the temperature control, the temperature compensation, all of this in one platform, I don't have to tell you, this is a massive, massive cost saving if you need to perform all of these measurements at the same time. Always happy to see the MPI putting a lot of pressure in the industry with bringing these latest innovations to market so we can do these complex measurements.
Hi, my name is Dustin Kendig from Microsense, and at Microsense we specialize in high-resolution thermal imaging. So high resolution in space, temperature, and time. And here at IMS we're introducing the application of our products towards antennas, gallium nitride transistors, and other power amplifiers. And so here we're working with ED Technologies for doing some antenna testing, where we have the thermal camera measuring the temperature with 50 millikelvin temperature resolution to detect small faults and to see which antenna elements are active or not active. And we can also use that temperature information to determine the electromagnetic radiation and power out of these different parts. So for this example, we're biasing a single element in this antenna, and we're biasing it, it's a 28 gigahertz antenna, and we can apply this to one of the elements, and you can see specifically which element is heating up. And if we were to do the full array, we could determine which elements are active and not active. From the thermal images, we can measure the temperature versus time down to 50 nanoseconds for the high magnification using a technique called thermoreflectance. And then we also have the infrared cameras that can image larger areas down to 17 milliseconds of resolution. And then the software allows us to look at the temperature versus time, so we can have the plot versus time for these different regions of the antenna array. And now I'd like to hand this over to Flavien from UMS to describe more about the application of the power amplifier and the device that's under test.
Hello, my name is Flavien Flores. I'm a technical sales engineer for UMS, and I'm here to introduce you to one of our parts, which is the CRC6054 QQN. It is a high-power front-end receiver which incorporates a transmit and receive path and a TR switch for telecom applications, radio systems. It is operating in the 24 to 35 GHz frequency range. Typically exhibits an RX gain of 18 dB with a low noise figure of 3.2 dB and a TX gain of 28 dB with 31 dBm saturated output power. This part embeds two technologies, which are gas and GaN technologies. This makes it a really good features for applications such as test and measurement, and also, of course, telecommunications.